Hello, I'm Jacob Crown. I'm a mechanical engineer at the University of North Florida.
Hi, I'm Peter Limos. I'm a mechanical engineer at the University of North Florida.
I'm Jackson Brooks. I'm an advanced manufacturing engineer at the University of North Florida.
A very brief introduction to wind turbines. Wind turbines use the power of wind to rotate very large blades, to rotate a low-speed shaft, which then goes into a gearbox into a high-speed shaft, which then goes into a generator to generate electricity. There are two main types of turbines called the hot versus vaught, a horizontal axis wind turbine, and then a vertical axis wind turbine. The horizontal axis wind turbine has its shafts horizontal to the ground, while the vertical has its vertical to the ground. Very simple explanation. So wind turbines are very green. They don't produce any CO2 emissions. However, they do have some effects to the environment, such as the death of flying animals, such as bats and birds. And they also produce quite a lot of noise pollution. So we had three original designs for our blades. As you can see, design one's on top. It was an 8-inch blade that uses airfoils that decrease in size as it goes along the length, with a 0.45-inch rod that connects to the hub. Our second design is more of a claw design that also uses airfoils that decrease in length as it goes to the tip. And then our third design was a thin at the base that increases in diameter, and then about a fourth of the way to the tip, and then decreases in size until it goes to a point around 8 inches long. For our blade design concept selection, we had 5 criteria. That would be weight, print time, material usage, lift, and complexity. The weight is how heavy the blades are. The heavier the blade, the more force it takes to move it. The print time is the fact that there's a limited amount of print time, so our designs have to be considerate of that. The material usage is that we have to weigh material and have an overall, try to lower the cost. So that's important. The lift created is the amount of aerodynamic lift that our blades create. It turns out that we didn't need any of that, so that turned out to be not that important. Complexity is how hard it would be to design. So it's not as important as everything else. It's just a personal restriction that we have. With all this considered, our first design was the best option. So I created a blade by first creating a 1/4-inch circle at the origin, and then I created 3 datum planes at 0.45 inches, 3.45 inches, and 6.45 inches. And then I drew 3 airfoils on the datum planes of decreasing size. And then I used a swept tool to sweep the edges so it all connects. And then I extruded and blended the edges of the circle into the blade. For printing these blades, we had some issues with the first blade. First of all, we printed it on its side so that the support materials actually stuck to it and we couldn't get them off. And it also, one of the corners was bent, and we determined the blade was also too small. So for the second print, we increased the size, the thickness, and we also printed it on its spine so that the support material wouldn't interfere with the sides of the blades. So after extensive testing, we determined that our original blade concept was not producing the desired output power. So we were forced to alter our original design. Through testing, we found that using the trailing edge as the leading edge produced significant more output power. We think it's because it's a sharp edge, which cut through the wind better. So in our new design, we used this information for our benefit. The new design uses a sharp leading edge along with a sharp trailing edge and a much thinner blade, and also shorter to reduce the weight. I designed it by creating a 1/4 inch circle with two datum planes that are at 0.45 inches and 3.45 inches, and then drew a needle-like design on the first one, and then a similar needle-like design, just half the size. And then I drew a line that goes through both of them, and then used a swept tool to connect the two, and then extruded and blended the connecting rod to it. So for our new alterations to our blades, we had some issues with printing. My original thought was to print the exact way that we printed the other blades, where we print it on the spine. But considering the fact that the spine is now a sharp edge, it did not have enough supports to support it, so it fell over mid-print. So for the second print, we printed at a 45-degree angle, so it had enough supports underneath so it wouldn't fall over, but then also the supports wouldn't interact with the face of the blade, so that we had a nice clean and smooth face to reduce the friction. With this final design, with the shorter, thinner, and wider blade along with the sharper edge, we saw a significant increase in power. These blades were designed to go really fast.
As for a base design, we had three main concepts. The first of which was a square pyramid design with a casing for a shaft to go through, which would be able to hold the blade hub and spin. And the second design was a square base with a hollow cylinder on top. And the third design was a circular base with 3 holes in order to hold the blades, which we previously printed, which would act as legs for the base. As for which one we selected, we decided choosing the cylinder with the blade legs as the bottom, as that one was the most efficient with our print time, as well as having a very stable base. The changes we made throughout this base design were we lowered the holes, which we initially set in the center of the cylinder. We lowered them closer to the ground so that the blades would be touching the ground. We created edge blends along the edges between the face of the base and the cylinder. And we also created an additional hole to allow the wires from the motor to follow through. Creating the base in CAD involved creating the sketch for the bottom of the base and extruding that, as well as creating the sketch for the hollowed out cylinder. Those were fairly simple, but it became rather complex when we introduced the holes in the sides of the bottom of the base. That required creating a datum plane on the plane of the base, of the bottom of the base, and creating it such that it is about a 1/2 inch lower than the plane itself, and then creating an intersection curve between that datum plane and the face of the extrusion, and then creating a pattern of the points along the edge of that intersection curve, and then creating holes from those points. As for the hub design, it was created in order to connect the base and the motor, which holds the blade hub and the blades. So as you can see, it has a hole in order to hold the motor and a rudder in the back in order to re-angle the blades so that they are properly facing the wind. As far as printing the hub, it went poorly the first 2 times because they were not the areas to hold the motor as well as fit into the shaft were too small, or rather for the shaft it was too large. So we needed to remeasure and reprint in order to make those fit properly. The second time we tried it, it also did not work. So the third time around, it worked well, but as you can see, the hub space was too large, so we just needed to fill it in with a little bit of tape.
For our final design, our hub design changed to meet different requirements. We had to increase the diameter to fit the motor. So the first couple of designs that we had, the hub ended up cracking because our motor didn't fit in. We kind of tried to force it in. We also had to decrease the size of the tube, which is kind of the extender that was on the bottom of the hub. It did not fit into our base design as intended at first. It was too narrow on the inside of there, so we had to lower the size of the tube. We also had to increase the size of the rudder. We had at first, on the first print, our rudder was the correct size and it worked fine. On the second print, the rudder wasn't big enough, so it didn't stop the size of the tube from going into the base design at all. So it just went all the way through and did not allow the hub to rotate. So we had to increase the size of the rudder on our final design for the hub. For our blade design changes, the initial design of the original blade was not producing the correct output power that we liked, so we had to shorten up the blade and change up the design a little bit to increase power output. Reaching the final blade design, we had to go through around 4 to 5 different designs in total to get to our final design. We had printing issues with that design because we didn't correctly place the blades into the software correctly. We had them set up, and with the different kinds of supports that we had also did not work, so it ended up tipping over and messing up the prints for all the blades. The final cost of our design was $30.31 with all the filament and all the different materials that we used to incorporate in our design. This slide here shows the motor testing that we did to try and figure out what kind of resistance produces the highest power output. What we did was we had a consistent stream of energy flowing through our generator, and we tested different numbers of ohms from 10 to 20 to 30 to 40 all the way up until 100. And from 40 to 60, we found that we had the highest power output, and we went by one, and we figured out that 59 is the highest number of resistance that we can have while also having the highest number of volts. This next slide, we did the same sort of testing with our blade design. We hooked up our blades to our blade hub, and we went around 4.5 to 5 feet, depending on which one we had to do for our final design, which ended up being 5 feet. And we tested the amount of power output that we got from the different blades. Here shows the different ways that we set the blades up. We did have different angles. We did not record those, but we had different angles set up, and we've deduced that the counterclockwise small three black and red blades produce the highest power output. To conclude the project, our design process throughout the whole thing, our biggest goal was to just produce the highest number of power output that we could, while still brainstorming new ideas for our design. Our initial focus was on our blade iteration, which was our old printed blades that we had before this process started. These blades were meant to increase the stability of our base design while also reducing the total print time, which in turn would also reduce the total cost we have. So this design helped us with 3 or 4 different criteria that we were forced to meet. Our base design was mainly focused on maximizing support and reducing total print time. For our blade design, we had a bunch of changes with those. We were basically just messing around with them until we found the highest number of volts that we could with the resistance that we had. We had around 4 to 5 different final blade designs, and we finally decided on our half red, half black blades that produced the highest number of power output. Our hub had a few different problems. At first, our hub, the part of the hub that connected the DC generator to the hub, was not big enough, causing a crack in not the first, but also the second design that we had. Our first design's rudder was also not big enough, so we had to attach tape back there to see if we needed a bigger design, which we did. So we ended up printing a bigger rudder also. During our testing phase, we started off with no hub or anything because we did not have that printed out and set up yet. So we tested it with just the blade hub, and we were trying to figure out the highest power output from that. Our power output started low with our first initial blade design, but after we introduced new blade designs, we showed a lot of improvement in our total power output. We noticed that the biggest thing was the actual blade itself. It wasn't the base design, it wasn't any of that, but it was the blades and how they were angled was going to affect the power output the most. For future improvements, I feel like we should have focused more on the hub design and kind of catch the errors before they came up, so that we can decrease the total prints that we had. If we were to do this project over again, I would focus on blade design more than anything else. I would add like a curve to the blades so we can catch air better and kind of increase aerodynamics. That was the team that ended up beating us. We got second place right to them. And that is the end of our presentation. These are the references that we used for our slides that we showed. And if there are any questions, reach out. But thank you very much. This project was a lot of fun, and I hope that I can do something like it again.